And I would like to start by thanking the organizers. That has been a great conference so far. I hope you'll enjoy it. And thank you for coming to this very last talk. So I want to start with some big questions that motivate my research. Some of these questions are there singularities in our universe? And by that, we'll see what we can answer. Maybe I can put the mic a little. So by if this question is kind of big, so all kinds of singularities, and we'll see what we mean later. If the area of the event horizon of a black hole, if it is increasing or decreasing, and this is connected with some big questions about the nature of black holes, such as the entropy and thermodynamics of black holes. The singularities, are they always hidden behind the horizon, or are they naked singularities, as we say? And about the total mass of a gravitating system, how is this defined, and is it always positive? So these are some kind of big questions that people have started looking for answers for them, maybe from the 50s and 60s. And I will try to answer them in this talk. So this talk is based on kind of a lot of work that started maybe back in 2018 when I was a postdoc in York. And I have a lot of papers that I will just put some snippets of them in this talk. The method that I will describe is in this paper from 2019 with Chris Fuster. But the results for particular theorems are in the later papers. So the talk is split into two parts: the classical theorems, because I want to talk about how the classical theorems work, and the second part is about semi-classical gravity, where we're actually working with quantum fields. However, it is not a quantum field theory talk. It's a very kind of gravity-based talk. So I'm only going to draw some motivation from quantum field theory. I have some other work that is more quantum field theory oriented. So let's start with the classical theorems. So first, the singularity theorems. I think I've talked about them a bit in the discussion sessions that I was in. So those define the singularities as geodesic incompleteness, so the geodesic end, and they're also inextendable. And these were derived by Hawking and Penrose from the mid-60s to 70s. There's the black hole area theorem, which was proven by Hawking, and it shows that the black hole event horizon can never decrease. The topology theorem was also proven by Hawking. It's the same paper, and it shows the topology of cross-sections of the event horizon. And the Penrose inequality that was motivated, not proven. So this is quite a little different, because there were quite a lot of assumptions in Penrose's kind of motivation and derivation. We're going to see some of those. And this is the relations between the ADM mass. There's mass missing here. The M does not stand for mass. It's a name. So it's the ADM mass, which is the asymptotic mass of a gravitating system, and the area of the black hole horizon. There's a positive energy theorem, which actually showed that this ADM mass is non-negative. And this was first proven by Shun and Yang, and there's a famous proof by Witten in 1981. So we have all these really nice theorems. These are all classical theorems. So these are for classical gravitation. And what I want to focus on for the first part of the talk is that some of those theorems, most of those theorems have a focusing theorem in their heart about focusing of geodesics. So this is what I'm going to talk about in the first part. So definitely the singularity theorems and the area theorem. I'm putting a star here for the Penrose inequality and the positive energy theorem, because only some versions of those have a focusing theorem. Other versions do not have a focusing theorem. So it kind of depends on the version of these theorems. So I'm mainly going to talk about the first three: the singularity theorems, area theorem, and Penrose inequality. At the end, I'm going to give some ideas about the positive energy theorem. So what is the focusing theorem? So this is a very, very schematic representation. Let's say we have a congruence of geodesics. It's like a, kind of a bunch of geodesics, very informally speaking, starting from some hypersurface. So usually we take the geodesics being normal to that hypersurface, and then there's something in that hypersurface that makes them converge. And then we might have some matter here, and that matter is generally attractive. It's like classical matter that behaves the way we expect it to behave. And so the geodesics continue to converge. We could also have some other weird matter that makes the geodesics diverge. And in this case, we don't have focusing. In this case, we have focusing, and that the geodesic end up having a focal point. So this is a very, very schematic representation. So let's be a little more exact about what a focal point is. So as I said, we have a hypersurface, S, and we have gamma, which is our geodesics, which is normal to that hypersurface. And the definition that I'm going to use is that after a focal point Q, the geodesic, I'm going to talk only about time-like geodesics here. I'm going to make some comments about null geodesics after, is no longer extremizing length. So you can think of a time-like geodesic no longer maximizing proper time, which is one of the main properties of time-like geodesic. If you're familiar with this, the actual exact definition of a focal point is where a Jacobi field becomes zero. If you don't know what a Jacobi field is, it doesn't matter. This is the definition that is important here. So let's see an example of a focal point in Riemannian geometry, which is always easier to visualize. So let's say we have a Riemannian two-sphere, and this is our hypersurface, the equator. So we have two geodesics starting normally from the equator. They start from points A and A prime. And here the North Pole is a focal point. And we can see how it's a focal point because if we follow this geodesic, this extremized length, so here is minimized because we're Riemannian geometry, so they minimize the length. So they minimize the length of the blue geodesic and the red geodesic up to point N. However, after point N, if we move past to point B, then they no longer minimize the length because I can take this shortcut and go from C to B directly without passing through N. So after passing through N, it's no longer minimizing the length. And the same thing happens in Lorentzian geometry, only doesn't maximize proper time anymore. So this is the property of the focal points. So the question is, how do you find focal points? We want to form a focusing theorem. So we want to state some assumptions and show that there's definitely going to be a focal point. So we want to find where the length is no longer extremized. So what do? We take the length of a geodesic. So this is the length of a geodesic as is defined for time-like geodesics in GR. And then we vary the geodesic, creating a family of geodesics. So how do we do that? Well, let's say this is our geodesic in the middle. And this is the tangent vector of the geodesic, which I call u mu. And then I take a transverse direction defined by another vector field, v mu, and I create this family of geodesics in the direction of this transverse vector. And now the geodesic is labeled by T, it's a time-like geodesics, that's the parameter on the geodesic, and S is the parameter of which geodesic we have in this family of geodesics that we vary in this transverse direction. So we vary this geodesic, and we take the first derivative of that length in terms of S, and then take the S to 0. If I do that, and I do a little bit actually of calculations, it's not super straightforward, but if we do a little bit of calculations for geodesics, we always find that this first derivative is 0. So this doesn't tell us anything. So we have to take the second derivative. So let's take the second derivative, and this second derivative of the length in terms of S, and then taking S to 0, this we call the index form. And this depends always on the variation vector on which transverse direction I took here. So the focal point test is going to be if this index form is greater or equal to 0 for some variation vector, then there exists a focal point. There's some a little trickier cases, marginal cases. If it's exactly 0, it's not before the focal point is not exactly at tau, etc. But it doesn't matter. The main point is the non-negativity of this quantity. So the next step is to actually compute this quantity and see what it is. So that's not an easy task. So after quite like a page of calculations, we get this result. So let's explain what it is. So the first part is just the derivative of the variation field v mu in the direction of the tangent, right? Remember that the u is the tangent and the v is the variation. And the second term includes the Riemann tensor. So you can think about how that comes about, because this is the length, right? So it has a metric. We take the second derivative, so we get curvature. So this term includes the Riemann tensor. And we also have a third term because we integrate by parts and we get a surface term. So that term only depends on the hypersurface. So we have these three terms. And now the next step is to pick our variation field V. So in principle, it could be anything. It could be just some transverse direction to the vector field U. But there is actually a convenient choice. So I take the hypersurface where the geodesic starts, the gamma of 0, and I take the orthonormal basis on that tangent space, where this is the 0 vector, so it's in the time-like direction, and it's the u mu, the tangent to the geodesic. So then all the other vectors, the space-like vectors, directions E1, E2, E3, are transverse to that time-like vector. And then I also take a smooth function, which is f of 0 equals 1, and this is f of tau equals 0, and then we sum over. So we take as a variation vector these three tangent vectors, basically. So we sum over them. And that simplifies things because if you remember here, this is the Riemann tensor here is there's the variation vector here is contracted with the variation vector. So if the variation vector field is just a tetrad, then we actually only get the Ricci tensor here. So it simplifies quite a bit. So the first term only depends on this function, and the second term depends on the Ricci tensor. Now the third term, which is the term that depends on the hypersurface, is the expansion of the hypersurface. So this is telling us something about the surface. So three terms, one just the function, the second includes the Ricci tensor, and the third is the expansion of the hypersurface. So we need three things to specify the sign of the index form. First, we need the sign of this term, because the curvature could be any sign in principle. So for that, the information we're getting is from an energy condition. I'm going to talk about that in a minute. The sign of K, that's the initial condition because it's about our hypersurface. I'm also going to talk about that in a minute. And then we pick the function. So the function we're free to pick. So we can pick a convenient function that gives us the result we want. So let's see about these first two things, the sign of R mu nu u mu nu and the sign of K. By the way, if you have seen the proof of this with the Rejzner equation, which is also showing the convergence or divergence of geodesics, this is an equivalent method. It's not different, but this method is much more convenient, as we're going to see later. So if you know exactly the sign of this quantity, then they're equivalent. If you don't know exactly the sign, but you have some average thing, this is more convenient. So what are energy conditions? Energy conditions are restrictions and contractions of the stress energy tensor that encode physical properties of matter. So physical is in quotes. I'm going to explain soon why. such as the positivity of energy. So the energy conditions are usually about the matter, but we also have their geometric form. So we have two energy conditions that are of interest here, the null energy condition and the strong energy condition, where they're for time-like vectors and null vectors. So the first line is the null energy condition. So this is the physical form, the form that we usually see this energy condition. So this is about the matter, because this T mu nu is the stress energy tensor, and it's contracted with two null vectors. And if you want kind of a physical intuition about it, you can use the perfect fluid stress tensor, and that is giving you the energy density plus the pressure is non-negative at every space-time point. So this is pretty reasonable for classical fields, at least. Now we have the geometric form, which we get from the physical form by using the Einstein equation. The Einstein equation connects the matter with the curvature. And this is the form that is used in any kind of focusing theorem, because that is what includes the Ricci tensor. And then we have the strong energy condition. So the strong energy condition, again, has the same geometric form, but now contracted with time-like vectors. But the physical form is a bit weird. And you might have not seen this quantity before, and it doesn't really appear unless you use the Einstein equation to go back from this contraction of the Ricci. So if you use the Einstein equations, you're going to get back to this. And here, T is the trace of the stress energy tensor. And the perfect fluid interpretation doesn't help very much either, because y the rho plus 3 times the pressure is non-negative. There's no very good physical reason. So the strong energy condition, it's actually much easier to violate than the null energy. If you want to learn more about energy conditions, Eric Curiel wrote a review about the classical conditions, and me and co-Sanders also wrote a review that has both classical and quantum. So what about the initial condition? This is about this K being negative or positive. So this is an important condition because this is what's telling us that the geodesics start converging initially. And we have one condition for null geodesics and one for time-like. So for null geodesics, we have what we call a trapped surface. So this was one of Penrose's big innovations when he wrote the singularity theorem, because it really characterized what a black hole is, I would say. The singularity is not what characterizes the black hole, I would say, but a trapped surface is what characterizes the black hole. So what is a trapped surface? A trapped surface is a null hypersurface that both null normals have negative expansion. What does that mean? Well, here is how the geodesics go, in particular, Eddington-Finkelstein coordinates in a Schwarzschild space-time. So we can see that easily. So the blue lines here are the ingoing null geodesics. So those behave as we expect. They're ingoing, so they go from outside and they hit the R equals 0. Fine, that's expected. But then the outgoing ones have a weird behavior. So the outgoing ones are the red ones. So the ones outside of the horizon, here is exactly the trapping horizon for a Schwarzschild black hole, which coincides with an event horizon. Here they go out, right? So that's what expected. You shine like light, goes out of the black hole, fine. But then when you go inside the event horizon, they have a weird behavior, which is that they all go inside and they hit R equals 0. So this is like shining a flashlight outside the black hole, and then the light turning back and going back to R equals 0. This is a very weird behavior. So this is a trapped surface. And the second one is for time-like geodesics. So this is a special slice with negative expansion. So this is actually what happens in cosmology, because this is kind of a cartoon of our universe. So let's say here we don't know what happens. And here the time-like geodesics kind of go out. They diverge, right? That's what happens in expansion. But we can take, because it's homogeneous isotropic, we can take these space-like hypersurfaces. We can foliate the space-time with space-like hypersurfaces. And if we take each of those and look in the past, if we look in the past, these hypersurfaces have negative expansion. So for the cosmology, you have to look in the past to have this convergence. But it's pretty much a similar effect that we have. One is for null geodesic, and the other is for time-like. All right, so let's go back to our condition for the formation of a focal point, where we have our two terms that we now know what they are. This is given by an energy condition, and this is given by the initial condition. So this is given by the time-like convergence condition. So this is one of the assumptions of the singularity theorem, in particular the Hawking singularity theorem for time-like geodesics, or any kind of theorem that uses time-like focusing. So this is the focusing time-like theorem, the time-like convergence condition. So this term is positive. Then we pick a function. So the convenient function here is just a linear function that satisfies these boundary conditions. And they have the negative expansion. So this is the space-like hypersurfaces with negative expansion that we have. And if we put these three assumptions, you can see here that the signs are specified. This is positive, this is positive, this we know what it is. So this condition is obeyed, and we have a focal point for any point tau that is larger than 1 over k. So with these conditions, we definitely have a focal point, and this theorem also telling us where the focal point appears, or maybe where after the focal point appears, not exactly where it appears. I want to say a few things about the null case. So for the null case, you might be worried that we don't have a length. That's not a problem. Instead of the length, we're using the action or energy integral, which is for any causal geodesics, so not an issue. We have a codimension 2 hypersurface. That's a bit more technical. We have the mean normal curvature instead of the expansion, also a kind of similar definition. And we are fixing the affine parametrization. So this is because for null geodesics, we can reparametrize the curve, and we can have a null curve with a reparametrized affine parameter. So here we want to fix the affine parameter because we want to have measure the length of the geodesic. So that works exactly the same way, only now this L has a meaning because we have fixed the affine parameterization, so we know how far the length is. So it's exactly the same thing for null geodesics. So this is the focusing theorem for null geodesics. All right, so how are these theorems used? We have our focusing theorem, we have our conditions, and it leads to the focusing of geodesics. So how this is used? So for the singularity theorems, we have the existence of a Cauchy surface. So there are also a few differences between different singularity theorems, but the main point of having global hyperbolicity is that focal points are not allowed to appear. It implies there are no focal points. So since there are no focal points, and our focusing theorem shows that there are focal points, this contradiction shows that the geodesic is incomplete. So since no focal points can appear because of the causality of the space-time, then the geodesic must be incomplete and inextensible, thus there is a geodesic. So this is how singularity theorems. The area theorem works in a surprisingly similar way, even though the result is very different. So how does that work? Let's see. So first of all, we consider not any null geodesic, but the null generators of the horizon of the black hole. So in particular, because we want to talk about how the area of the horizon changes. So this calligraphic H1 is the horizon, the event horizon of a black hole at a snapshot of its evolution. So first we assume, again, it works with contradiction. We assume that this is negative. So this is K. It's the expansion of the mean normal curvature, because we're talking about null geodesic of the hypersurface. Now, this is a little sketch of what's happening. So this sigma 1 and sigma 2 are Cauchy surfaces. This is the event horizon, which is designated by H. And the this cross-section of the horizon, the H1 and the H2 is like snapshots in time of the event horizon as it evolves. And these dotted lines, you can think about them as the null generators of the horizon. So we have assumed that this is negative, but we have the causality condition, which here is actually stronger than global hyperbolicity, is a strong asymptotic predictability, which is, it's a complex definition, but the main point is that it's asymptotically flat and there's no naked singularities. So it implies the existence of an event horizon. It guarantees the existence of an event horizon. So this also implies that there are no focal points. So since there are no focal points, but this telling us that there are focal points, then we also create a contradiction. And so this is always non-negative for the null generators. So we can write down the change of the area of the event horizon, and that depends on the L. Sorry, there's some typos here. So this is L. So this is L mu K mu, and this is always non-negative. So, so this telling us that the horizon always increases. Area of the horizon always increases. So this is actually the same conclusion. It uses the exact same argument as the singularity theorem, but it comes to a very different conclusion. So this is for the area theorem. Let's see the Penrose inequality. So for the Penrose inequality, we have a few more assumptions. So let's follow Penrose's thinking. So we have a focusing theorem, exactly the same, Cauchy hypersurface. That means we have a singularity according to Penrose's singularity theorem. We are assuming the weak cosmic censorship. The weak cosmic censorship is that the singularity is behind an event horizon. Then the area theorem holds, since we have the focusing theorem. So the event horizon of a black hole is always non-decreasing. All right, so now we follow the thinking of Penrose. The black hole spacetime settles to a Kerr black hole. So this is another assumption. And then this is what we have. The area of the horizon, because of the area theorem, is always less or equal than the area of the horizon of a black hole, of a Kerr black hole. The area of the horizon of a Kerr black hole, we know exactly. We can write it down. This is the area of the horizon of a Kerr black hole. This is the mass of Kerr, and this is the angular momentum. All right, we know it exactly. So we can write it down. This is just algebra, is less than this. And now we're using the definition of the asymptotic mass of the space-time. So, here we have a Bondi mass and the ADM mass. So the Bondi mass is the asymptotic mass of a gravitating system at null infinity, while the ADM mass is a space-like infinity. So there is, it's actually in static cases, this is an equality. And that leads us to a relationship between the ADM mass and any cross-section of the event horizon. So the idea of Penrose was, well, we can maybe test that for black holes. If we have just the mass, the asymptotic mass of the space-time and the horizon, we can test this inequality. And if this inequality is violated, then maybe the most reasonable thing that is violated is that is the weak cosmic censorship. The singularity is behind an event horizon. So the singularity is not necessarily behind an event horizon. So it's like a test of weak cosmic censorship. It's not a proof of weak cosmic censorship. So if this is obeyed, it doesn't necessarily mean the weak cosmic censorship is obeyed. So, it's just a test. So that's how it works. It also works with the focusing theorem. Now, I said there, I put a star there because there are other proofs of the Penrose inequality that use initial data formulation and do not use this kind of thinking exactly. All right, do you have any questions? Yes. Maybe we can have one here if it's like.
Okay. When you were explaining the area, when you were explaining the area,
Yeah.
You were also explaining you have the null generator of the horizon. Is the expansion of this generator on the event horizon always 0?
Sorry,
Is
can
the
you repeat that?
expansion of the null generator L always 0 on the event horizon?
No, no, no. It's so these are the null generators, right? That are null geodesics, and we have this is the so this is the tangent vectors to this geodesic, and this is the mean normal curvature, which is a time-like vector field, right? So so this inner product we assume that is negative, but it ends up being non-negative. Yes. So it's not 0 necessarily.
No, I was meaning about the expansion of this vector field.
The expansion of the vector field. Are you thinking of theta?
Yes.
Yes, theta is actually can be defined using the k, using the mean normal curvature. Maybe I can show you the definition later, but they're exactly connected. Okay. So, and you have to also think about the theta plus and theta minus, so the ingoing and the outgoing.
Yes, I was thinking about the theta plus.
Yes, yes, one of them it is 0, correct, but the other one is not.
Okay. And the second question is, in the next slide, why is the ADM mass entering here and not other concepts of mass like the Hawking mass?
So here I think Penrose was thinking of a static black hole. Oh, wait, sorry, stationary, not static because it's Kerr. So you think of a stationary black hole. So it's kind of a classical proof. So for a stationary black hole, you can define no problem the ADM mass.
Okay, thank you.
But I believe there are some formulations that use the Hawking mass. All right, so let's move to the second part, which is about semi-classical gravity. So first, what is semi-classical gravity? So the main question that motivates my research is, do these theorems generalize semi-classical gravity? So semi-classical gravity is basically having quantum fields. So having quantum fields on a classical curved background. So instead of having the Einstein equation, we have the semi-classical Einstein equation. This is an approximate equation, clearly, because we have not quantized space-time at all. We don't have discreteness or anything that other people talked about. So this is our usual Einstein tensor. But on the left-hand side, we have the renormalized stress energy tensor. So this is a quantum object. This is quantum fields, and we take out the infinities, etc. We take a state. So this is quantum fields generating a classical curved background. So this is, as I said, this is clearly an approximate equation with a certain range of validity. Probably the most famous example of where this holds is the event around the event horizon of a black hole, because there the curvature is still classical. It's not a very large curvature, but we still have quantum effects. We have Hawking radiation. So quantum effects are important. Maybe quantum effects are also important in other places too. So so this is kind of where we're thinking about that. Quantum effects are important, but the curvature can still be treated classically. I mean, ideally, we would like to solve that and find exact solution. But we have very, very few cases where we have solutions of this, mainly in cosmological space-time, very, very high symmetry. So here, all these theorems, you might have noticed, I did not define a metric. There is no metrics, there is no symmetries. This is kind of the power of these theorems. So I do not expect to derive exact solutions. So, so we'll see in a moment what I'm going to do with this equation. So first of all, why don't I use the old theorems? Well, I cannot use the old theorems because of the energy conditions. So the positivity of the energy density is incompatible with quantum field theory. So if you haven't heard of that statement before, this is kind of an important takeaway from this talk, that the positivity of the energy density and similar quantities like the null energy condition, etc., is not compatible with quantum field theory. We can have negative and positive values in a spectrum of observables. So this is a very old result from 1965. And so we cannot have the old theorem for sure. So I cannot just take these conditions that we had and put expectation values around and be like, oh, okay, we're done. I cannot do that. So what is my strategy? My strategy is to use average conditions, to use integrated conditions. So the step one is to replace the pointwise condition with an average one. So here we're still in classical curvature. So we have integrals, either over time-like or null geodesic, and we have some negative bound on the right-hand side. So I don't know what this A is yet. The second step is to find the condition obeyed by quantum fields with the same kind of bound. So similar to A that we have here. So here we have the strong energy condition for matter, the null energy condition for matter. And here I take the expectation values and I have this averaged over. So, and some function, I can have some function here that shows how much of the geodesic we're integrating over. And here's how I use the semi-classical Einstein equation, very, very simply, to make a connection between these two kinds of conditions. So I'm not solving the equation or anything like that, but I'm just assuming that these quantum fields that I have do generate this classical curve background. And so I make a correspondence between these quantum expectation values and these classical curvature quantities. So the idea is to derive these conditions for quantum fields, to use the semi-classical Einstein equation and prove the theorems. Or you can work the other way around, prove the theorems and then find the condition. So you can go kind of either direction in these steps. So the next question is, do quantum fields obey this kind of condition? Like, should I even expect quantum fields? We know that they don't obey these pointwise conditions on every space-time point, but do they obey this average condition? Well, the answer is probably, because we have some good evidence for that. And this comes from quantum energy inequalities that were introduced in the 70s by Larry Ford. And they introduced a restriction on the positive magnitude duration of energy densities. So really the quantum energy inequalities are telling us that, okay, this object can be negative at points, and it can be negative maybe on average, but there's a lower negative bound on average. And we've seen that this actually holds for a variety of quantum fields in a variety of backgrounds. This is one of the first quantum inequalities and probably the most famous one that were derived. So this is for a free quantum scalar that is non-minimal couple on Minkowski. So this is a very, very simple case. And we are averaging over time like geodesic. And this is none of the two energy conditions, actually. This is the weak energy condition. So this is just a stress tensor contracted with two time-like vectors. Okay, so it's not exactly what we want, but it kind of shows us what conditions the quantum fields obey. So the other thing we observe is that the lower bound only depends on this function f. So not on the state. This is very good because it's a bound for all states. And this is the kind of bound we want to have. It actually doesn't hold for all quantum fields. But we do want to have this lower bound. So what is this function f? It's a function with compact support or a function that drops sufficiently fast so that it tells us what part of the geodesic we are picking. So let's take the support of the function to be T0. And then the right-hand side becomes minus c over T0. That c depends on what kind of function we pick. For example, Lorentzian or Gaussian or whatever. So this is telling us that if we take a very large support, so if we take almost the entire geodesic, that goes to 0. And if we take a very small T0, then that goes to minus infinity. So we have this relationship between the length of the geodesic and the support of the negative energy. So not a lot of negative energy for a short time, but a lot of negative energy for a short time, but not a lot for a long time. And so we have this weekend condition inspired by quantum energy inequalities. So the word here is inspired because it has not been derived for all fields clearly, but it has been derived maybe for some fields. So this is the kind of condition that I'm going to use from now on. So this is the end of the quantum part. So from now on, I'm just going to keep being completely classical, but with this condition that I'm hoping I can get from quantum fields. So what is the bound of this condition? This m is an integer, so I can have any number of derivatives on f, and this is a term with no derivatives. So this qm and q naught are unknown from in what follows. And in the cases that we have been derived from quantum field theory, this qm and q naught would be things that depend on the quantum field. So in the quantum inequalities we have derived, they depend, for example, on the mass of the field, or maybe some maximum value of the field and things like that. Yes?
The weakened energy conditions. First of all, this is for a time-like vector field?
So this is for time-like, let's say, yes.
And there's a version for the null as well?
There is a version for the null. Each of them has their own problems.
Okay. So the average null energy condition, of course, has been used for several of these singularity theorems and focusing theorems.
Sort of. Just to make a comment on that.
Yeah.
The average energy condition is a great condition. It has been proven in a lot of ways, but it cannot be used in these kind of singularity theorems because we start from a hypersurface. So we definitely have a starting point. So we cannot have an entire null geodesic. So the null energy condition, the average null energy condition has only been used in the cases where we have conjugate points. So we don't have a starting point. So this is the motivation for using this kind of condition. And the other motivation is because we can derive them from quantum. So this is our favorite condition for the formation of a focal point, exactly the same. And it has this function that I showed you before that has this boundary condition, the 1 and 0. And then we have the energy condition. This is our energy condition. And initially we're like, oh, that's great. We have F here could be the same F. Well, it can't be the same F because of the different boundary conditions. Because as I told you, for the energy condition to be finite, we need a function with compact support or that drops sufficiently fast. So we have different boundary conditions for this function. So what do we do? Well, what we do is pick two functions. We have two functions, the phi, which starts from 0 and goes to 1, and the f that goes from 1 to 0. So then the energy condition is the product of these functions, and that satisfies this condition, that's fine. And then the focal point has only the function f, which also satisfied the conditions that we have. So what do? Well, we take this condition and we plug it in here. And we find what k we need. So this is the strategy. And we could optimize this function f and phi, which we have done for m equals 1. We haven't done it for general m, actually. If mathematicians have some idea of how to do that for general m, let me know. But for general m, we just picked some functions because you don't have to optimize, you can just find a function. So the only thing that remains is that because here this goes from 0 to 1, and here we only have the function f, we have to estimate the energy density or whatever quantity we want between 0 and tau naught. So this we estimate by some energy density or effective energy density rho 0. So our k, this k comes after plugging in this here, we end up with this k. So to have a focal point, we need the k to be less or equal than this function minus mu. And now that function depends on all these things. The qm, the q naught come from the quantum field theory maybe, how far the focal point is, the tau naught, the rho 0. So it depends on all these things. So instead of having k less or equal to 0, as we had in the classical theorem, we have k less or equal to minus f function. And this is the status of the theorems. So for singularity theorems, we have singularity for surfaces with k less than minus nu. For the area theorem, it does not hold, so it doesn't give the same thing for quantum fields. It doesn't tell us that the area of the black hole horizon is always increasing. This is very good, actually, because otherwise we wouldn't have Hawking radiation. But we have a bound on the evaporation rate. So the bound on the evaporation rate is again nu. I have one more slide. And for the Penrose inequality, we have something slightly different. So here we have this trapped surface, which has k less than minus nu. So it's a different hypersurface here. It's not the marginally trapped surface. And we don't have an end point of the evaporation. So this is for evaporating black holes. So remember Penrose was like, well, the black hole settles to a Kerr black hole. We can't say that for evaporating black holes because the horizon shrinks continuously. So there's no end point. So what we do is to take two hypersurfaces that are distanced s from one another. So this bound is for two hypersurfaces that we pick. So we have this kind of inequality. So it's a modified Penrose inequality. And I wanted to say one word about this hypersurface. So this, we call it the sufficiently trapped surface because it's a hypersurface which is sufficient to lead to geodesic incompleteness with this average condition. And if we have an evaporating black hole, this marginally trapped surface, the trapped surface with k equals 0, that can be outside of the event horizon. So this is the case where the null energy condition is violated. But the sufficiently trapped surface is always inside the event horizon. So this is the hypersurface that we are considering. And here I have some results for other theorems. I think the slides will be uploaded so you can look at these other theorems and some of the results that have been proven with average energy condition. And for the positive energy theorem, I didn't talk about it, but I'm currently doing some work with my PhD student Joshua Proctor and Eduardo Hefman from Hamburg. So I hope to have some results soon for the positive energy theorem. The positive energy theorem, the version we're looking at, is not actually a focusing theorem, so it needs slightly different techniques. And these are my conclusions. One of my questions is what Sumati asked about the conjugate points. So the conjugate points are slightly different than focal points because we don't have a hypersurface. We have 2 points. And those are trickier to do with these kind of conditions. And I wanted to put a thing because there's some people working on low regularity space-time. Well, Anna Greta, I think, maybe it's the only person here. But there are some other people, and these techniques are kind of similar actually, because you can have point-wise energy conditions in low regularity. And if the organizers allow me, I have an advertisement. I'm one of the organizers of the Semi-Classical Online Network Exchange, or SCOON. So we organize online seminars once a month, so they can be attended from anywhere in the world. We also have speakers from everywhere in the world, and we probably will have some in-person events in the UK actually next year, but the online seminars continue. So thank you very much.
Thank you, Eleni. Are there questions?
Thank you. It was very inspiring. I recognize Sasha's things. Can you tell more about the difference between conjugate points and focal points?
Yes. So the main difference is that in the focal point, we had this hypersurface S, right? And we have the geodesics being normal, and then we have the focal point. But when we have conjugate points, we have a geodesic, and we have 2 points on the geodesic. The condition is relatively similar, but we don't have this boundary term that I showed you. So we don't have the term about the hypersurface.
Is it the difference that in the case of conjugate points, you are starting with a variational curves which have 0 as a variational vector, field at the beginning. So the
You mean
Jacobi
the,
field
you
is
mean the
zero at
vector
two-
field V?
Yeah, so
No,
it's
no,
zero at the 2 point, while in the second case, it's zero only.
Yes, yes,
in the
you
ending
mean
point.
sorry, you mean the Jacobi field?
The Jacobi
Yes,
field.
yes, it's zero in both points, yes. Exactly.
Yes, which means that the variational curve starts from fixed points, and there is a variation in this sense.
Yeah, there's a
While
variation.
in the second case, you are taking some kind of parallel variations because you are taking a direction.
Yes,
This is the difference?
yes.
Thank you very much.
Thanks a lot for the super nice talk. I have a question about a couple of slides ago. Could you please explain why a marginally trapped surface can be outside of the event horizon? Because
Yes,
naively, I would expect that if you have some horizon that is evaporating, it would be time-like, and so that it would be lying inside of the event horizon, not outside.
yes, it can be. That is very true. So this marginally trapped surface can be outside or inside the event horizon. So here I just drew one snapshot, possible snapshot of the evaporation.
But
So it can be either. But at some point of the evaporation, there's a kind of evidence for that. That at some point of the evaporation, the event horizon is under the marginally trapped surface.
But how? Because as I was saying, right, the event horizon is null, and the marginally trapped surface, if you have an evaporating black hole, would be time-like, right?
Why?
Because if you have if you have something that is growing, then you have a space-like surface, and if you have something that is evaporating, you have a time-like surface.
I'm not sure I agree. Maybe we can talk about this a little later. But there's definitely papers that show evaporating black holes and the marginally trapped surface being outside the event horizon in this case. But yeah, maybe we can talk about it.
Other questions? Okay. If not, then let's thank Eleni again. Since this was the last talk of the conference, we should take the opportunity to thank all of the organizers for bringing us here for this very nice conference. Let's put a